All right, IB Chem students, this is my second crack at this because it's my first time using this software, but hopefully it'll work this time. So this is a video lesson on Lewis structures. Those of you who were in class on Monday already saw me talk through at least the first 4 slides of this PowerPoint, so just bear with me, or maybe, speed it up through the first little bit. The topic from the IB Chem guide, so topic 4.3, Lewis, aka electron dot structures, show the electron domains in the valence shell and are used to predict molecular shape. So here we're really focusing on valence electrons and how they are involved in bonding. And then all the different ways that electrons can be sort of attached to an atom, either as part of a bond or as just sort of a lone pair stuck on. The general term for that is electron domains. It's not a term that I find I use a lot, but IB does like that term, electron domains. So we'll come back to that a couple times. And then the predicting molecular shape part, that is part of topic 4.3 that we're not going to get to in this lesson. There'll be a second set of videos dealing with VSEPR theory, which is the tool we're going to use to predict molecular shape. Looking at the specifics of the Chem Guide, we've got our understandings here. So the things in red are the things that you should be comfortable with by the end of this video. So we're going to start with the basics of drawing Lewis dot diagrams or Lewis structures, which means focusing on the octet rule. Then we're going to look at some exceptions to the octet rule, both incomplete and expanded octets. And we're going to look at this idea of resonance structures. Okay, so by the end of the video, you should be able to deduce a Lewis dot diagram for a wide variety of molecules, not just simple ones where the octet rule is followed, but also things like polyatomic ions, things where you have a choice where the double bond might go, that creates resonance structures, and things with expanded octets. I think I already said that. Okay, so let's start with an example. Now, as we look at this, it's maybe not a bad idea to pause the video, grab yourself a scrap piece of paper and a periodic table. Those are 2 things that could be helpful to have on hand, as well as a pencil. I'm going to recommend a pencil because sometimes when we're drawing Lewis dot diagrams, it actually is necessary to sort of go through the steps, and then we realize that we've got to erase something to sort of refine our structure. So using a pencil gives us that freedom to erase rather than scribbling out and redrawing, which takes a lot more time and looks really sloppy. So maybe you pause the video, you grab some scrap paper, but let's get started on this. So we're going to draw what I think is the simplest type of Lewis structure. It's only going to have single bonds in it for carbon tetrachloride. And I'm going to give you sort of a set of steps that you can follow for a situation like this. So the first thing we're going to do, we're going to total up the number of valence electrons that all the atoms...
Naheed Kadri, please come to the office. Thank you.
You know what, I'm just going to leave that in. Makes it authentic. We're going to just total up the total valence electrons from all the elements that make up our molecule here, all the atoms. So we've got carbon, and this is where the periodic table comes in handy. We're pretty much always dealing with non-metals here, so you can look at the group that the element is in. So carbon is in group 14, and then you can subtract 10 from that group number to get the number of valence electrons. So carbon brings 4 valence electrons. Similarly, chlorine in group 17, it's going to bring 7 valence electrons. So that gives us this calculation. So we got 4 valence electrons right here from our carbon, and then there are 4 chlorines, each one brings 7, so that gives us a total of 32 electrons. Now we're not going to really, from here on out, focus too much on which atoms brought which electrons with it. All we really need to know is that the total of the electrons is 32. That's sort of going to guide us, give us a check for whether or not we've drawn our structure correctly. Okay, so from there, I want to arrange my elements because a Lewis structure is a 2-dimensional representation of the molecule. It shows the bonds where the valence electrons go. So I want to arrange my elements in such a way that sort of makes sense. So and one good guiding principle for this is we want elements with lower electronegativity. They should go in the middle. So here we've got carbon, we've got 4 chlorine, so there's 5 atoms in total. Something's going to go in the middle. Everything else is going to be sort of organized around that. And then if I compare carbon and chlorine, I could pull out table 8 from my chemistry data booklet, or I could go with sort of the more wishy-washy way of explaining electronegativity, which is just that it's higher towards the top of the periodic table and higher towards the right. So if I compare carbon and chlorine, carbon has lower electronegativity, chlorine, a halogen, has higher electronegativity. So I'm going to put carbon in the middle, and then I'm going to put the chlorines around it. Okay, that looks like that. The shape actually doesn't really matter for Lewis structures because it's only a 2D representation of something that's actually 3-dimensional. So don't worry too much about angles or spacing or whatever. Just arrange it so it looks pretty logical. Next thing we're going to do is draw single bonds between adjacent atoms. So I like to, when I'm drawing my Lewis structures, represent my bonds with sticks. You do have the option of using dots or even like a pair of a dot and an X. But I just find sticks look neater and they're much faster to draw when you're doing this by hand. So that's going to look like that. So my chlorine and carbons are adjacent and I'm putting sticks between them. Okay, so this, and each of these represents 2 electrons, right? Because it's a bond between chlorine and carbon. So 2 electrons to make up that bond. The next thing I'm going to do is I'm going to fill everything's valence, okay? And I'm going to use the octet rule to guide me there, assuming that, for now, every element wants to have 8 electrons to have a stable filled valence shell, okay? Now carbon, because each of these bonds contains 2 electrons, carbon already had a full valence or a full octet. But the chlorine, each chlorine needs an extra 6 electrons to get a full valence, okay? So everything's octet is satisfied. The next thing I need to do is total up how many electrons I've represented in a diagram. And I'm going to recommend that you pause the video here and take a second, look at the diagram, count up the electrons yourself. So welcome back if you followed my advice and you paused it. And hopefully you got that there are 32 electrons. Okay, and that's really ideal because I started with 32 valence electrons. I have 32 electrons represented in my diagram, which means that it's correct. I followed these rules, making sure to put the element with lower electronegativity in the middle. My Lewis structure is probably correct. Okay, so that one's good. We're gonna add a small level of difficulty here. We're going to try an example where we need multiple bonds. And this is where having something you can erase as you go is helpful. So carbon dioxide. Now, I want you guys to bear with the steps as you watch this. You probably already have an idea of what the Lewis structure of carbon dioxide looks like. You know that there are double bonds. But I want you to sort of see the logical progression that gets us to those double bonds rather than just drawing it from memory. Because there are going to be situations where you need to be able to follow the steps. You won't just know what the structure is supposed to look like going in. Okay, so we're going to start the same way we did with carbon tetrachloride. We're always going to start our Lewis structures this way. We're going to total the valence electrons. In this case, we've got carbon once again, which brings 4. Oxygen, which is in group 16. Each oxygen has 6 valence electrons, so that gives me a total. 4 plus 2 times 6 is 16. Then I'm going to arrange the element symbols in a logical way. So once again, oxygen is the more electronegative element, carbon less, so I'm going to put carbon in the middle, put the oxygens on either side. Okay, that looks like that. Then, hopefully you remember, next step, draw single bonds between adjacent atoms. So that is going to look like this. I'm using sticks once again for my bonds. And then I'm going to fill everything's valence. So I'm still using all the same steps I used in my previous example. Okay, so non-bonding pairs means I'm going to pair up my electrons. I'm going to make sure everything has a full octet. So that's going to look like this, and then like this, and then like this. Okay. And then we do the next thing on my list, which is to check the total. Okay, so I'm going to ask you to pause the video and do a check yourself here. And welcome back, and hopefully you found that you have 20 electrons represented in this diagram, which is not the correct number. I'm supposed to have 16 electrons. So I need to figure out some way to reduce the number of electrons in my diagram, but I can't break the octet rule. I need everything to have a satisfied octet, okay? There are going to be some exceptions to that, but carbon and oxygen aren't elements that make those exceptions, okay? So I've got to make sure everything's octet is still satisfied. So I'm going to use a strategy of making multiple bonds. The way I do that is that I'm going to erase the non-bonding pairs on two adjacent atoms. So like that. And then I'm going to replace that with a bonding pair. Okay, so you can check here that carbon's octet is still satisfied. It's got 2, 4, 6, 8. Same with oxygen, 2, 4, 6, 8. But now I've got fewer electrons. I've actually only got 18 now rather than the 20 I had before. But that's still not the right number. The number I want is 16. So then I'm actually going to repeat that process. I'm going to erase 2 non-bonding pairs and replace it with a bonding pair. Keeps everything's octet satisfied, but it reduces the number of electrons represented in my diagram. And then I end up with 16 electrons. So this appears to be the correct Lewis structure. Okay, I'm going to pause it there, and I'm going to make part 2 of this video. That's going to start in on some sort of little details that we sort of glossed over here.